Today, we're going to take a look at exponential relationships. If you remember way back to September, that's our second unit, growing. And we're going to take a quick little meander through what it means to be exponential. And in a separate video, we'll also talk about exponential relationships and what's happening today and why is it important. So the first thing we're going to talk about is exponential relationships and growth in relation to the table. What is happening for an exponential relationship? So in an exponential relationship, we are multiplying the initial value by the same thing every time. So in a linear relationship, you are adding the same amount or subtracting the same amount every time. In exponential relationships, you are always multiplying by the same amount every time. So if we were to start with, let's say we start with 3 cases of COVID-19, and COVID-19 has a growth rate, and the growth rate is what you're multiplying by every time. So COVID-19 has a growth rate of roughly 2 new cases for every case that you already have, and that happens every 3 days. So it's doubling every 3 days. So if you start with 3, after 1 doubling time, that's 3 days, you'd have 6. After a second doubling time, that would be 6 days, you'd have 12. After a third doubling time, that would be 9 days, you would have 24 cases. After a fourth doubling time, you would have 48 cases. Now, 4 doubling times in the case of COVID-19 is 4 groups of 3 days. So that's in 12 days. Notice how in 12 days, you've gone from 3 cases to 48 cases. That's 16 times the number of cases in just 12 days. Exponential growth happens very, very quickly. So if you look at the graph of exponential growth, you'll see that originally the growth looks pretty small, but then at some point it just takes off and it's really hard to control. So if this is the value of your money that you've invested, that is very, very good. If it is the number of COVID-19 cases over time, that is very, very bad. Exponential relationships come in 2 types. They come in growth, where it's obviously growing, or exponential relationships can decay. In other words, they can get smaller every time. So we see this an awful lot in the case of, say, population extinction, or if we talk about medicine in the blood. So medicine, when you take medicine, it goes into your bloodstream, and then your liver starts breaking down that medicine and becomes less and less effective. I'm sure all of us have felt that during a cold that we've had. We took some cough medicine. It works great early, but then it doesn't work so well pretty quickly. And so if you have, say, 24 milligrams of cough medicine in your bloodstream, and the decay factor, the amount that is going down by every time, is 1/2. So if you're losing half of that, or your body is processing half of that medicine every hour, so then after 1 hour, you'd only have 12 milligrams. After 2 hours, you'd have 6. After 3 hours, 3. After 4 hours, 1.5 milligrams. So you can see that's kind of the opposite of what's happening here. Over here, you see that it's growing fairly slowly, and then it starts growing really, really rapidly. In this case, you lose a lot initially, and then the loss is smaller every time. Exponential decay in its graphic form looks like this. Now, you may be thinking, exponential decay and inverse variations, the graphs and tables look very similar. Here's how to tell them apart. Exponential decay will have a y-intercept. You have to have an initial amount, an initial value, in order for exponential growth to happen. Just like in the graph, the table will have a y-intercept as well. Inverse variations do not have that. Also, if you look in the table, if you multiply 1 times 2, you get, 1 times 12, you get 12. 6 times 2, again 12, but 3 times 3 is 9. Inverse variations, no matter where you look on the table, when you multiply the x and the y together, you will get the same value. So that's one quick way to tell the difference between exponential decay and inverse variations. So let's talk about the equations of exponential relationships. First, growth. Exponential relationships are always written in the form of y equals a times b to the power of x. So an exponential relationship will have a variable that is an exponent. Well, what does a and what does b represent? So the a value is the initial value. That's how much you're starting with. So if you're talking about an investment, that is the initial amount of money that you invest. It's your y-intercept. And then the b value represents the growth factor. The growth factor is what you are multiplying by every time. So if I'm looking at this table right here, my y-intercept is 3. My growth factor, well, it's doubling every time, so my growth factor is 2. Therefore, the equation for this table is y is equal to 3 times 2 to the x power. Let's take a look. 2 to the first power is 2. 3 times 2 is 6. 2 to the second power is 4. 4 times 3 is 12. 2 to the third power is 8. 8 times 3 is 24. And we can continue in that manner. Well, what is the difference in the equation between growth factor and our growth rate, or exponential growth, and exponential decay? That lies in the growth factor. Now, for you to have exponential growth, you need a y-intercept that is greater than 0. And it's just straight up greater than 0. And that makes sense because if you start with nothing of something, it can never grow. There's no initial value. The growth factor has to be greater than 1. If you have a growth factor of 1, then you're always multiplying by 1. And if you multiply something by 1, it doesn't change. That differs for exponential decay in that you still have the a is equal to b, or y is equal to a times b to the x. However, and a is the y-intercept, but b is the decay factor, and the decay factor has to be less than 1. If you multiply by a fraction that is less than 1, you will get a smaller result, a smaller product. The y-intercept, again, has to be greater than 0. Otherwise, it doesn't make sense at all. All right, so we've talked about the equations here. So let's try to figure out the equation for this table. Well, our y-intercept is 24, so our a value should be 24. I'm multiplying by 0.5, so my decay factor should be 0.5. And there we go. Now, when we deal with exponential relationships, we are always talking about growth factors and decay factors, but unfortunately, in the real world, you rarely hear people talking about decay or growth factors. You'll always hear about decay rates and growth rates. Things get reported as a percentage, a rate. So we have to spend some time talking about how to convert growth rates and growth factors. Well, if we have a growth rate of 4.75%, let's say it's a city sales tax, what does that equate to in terms of growth factor? Well, if I multiply by 4.75%, I will not get a larger number, but we're supposed to be growing, right? So we have the equivalent growth rate of 1.0475. Well, what does that mean? This 1 represents the initial value. In terms of tax, this is the 1 represents the cost of the item, and the 0.0475 represents the additional tax that you must pay on the item. Or a little more fun, if you have a savings account that has a 4.75% return, which would be unbelievably wonderful. If you ever see that, definitely use it. Then the amount you invest would be that 1, and then the amount that you earn in interest would be the 0.0475. If you have a 5% growth rate, then your growth factor would be 1.05. If you're growing at 50%, that'd be 1.5. Please notice the difference between 1.05 and 1.5. 1.05 is the 5% growth, 1.5 is 50% growth. That stands to reason that 1.75 represents a growth rate of 75%. Now things get a little bit weird when you start talking about doubling. A growth factor of 2 represents a growth rate of 100%. That means you are doubling every time. So if I look here, we have a growth factor of 2. That means we have a growth rate of 100%. Finally, if I have, let's not do that one. All right, so how do we turn a growth rate into a growth factor into a growth rate, or vice versa? So what am I doing here? So I'm taking our growth factor, let's say it's 2. I'm subtracting 1. I'm always subtracting 1. So 2 minus 1 is 1, and then I'm multiplying it by 100%. And that will give me my growth factor. 2 minus 1 is 1 times 100 is 100. Let's take a look at this one. 1.75 minus 1 is 0.75. 0.75 times 100 is 75%. Converting decay factors into decay rates, and back again, is a little trickier. Growth rates, we're always just getting bigger, which makes life a little bit easier in this conversion. But when we're talking about converting decay factors into decay rates, we have to remember that a decay factor represents what remains. So the decay factor will tell you what percentage of your initial value will remain after one set time period, whereas the decay rate represents the amount that is taken away. So let's see how this affects our numbers. If we have a decay factor of 0.98, that means that 98% of whatever we're talking about, say flea medicine in the dog, if we think back to our investigation and growing, if 0.98%, if 0.98 remains, that means 2% of the medicine has disappeared, has been taken away. So a decay rate, it's always great when you find typos and you're making a video, right? So if your decay factor is if your decay factor is 0.98, your decay rate is 2%. Well, if we have a decay factor of 0.75, if 75% remains, that means we're taking away 25%. If we have a decay factor of 0.5, we're taking 50% away, or sorry, 50% remains, which means we're taking 50% away. And finally, if we have a decay factor of 0.15, 15% remains, which means we're taking away 85%. So this idea of what remains and what is taken away in relation to factors and rates is super important to keep straight. So how do we convert it to, you gotta love working from home with yelling kids, right? So decay factor is going to be equal to 1 minus the decay factor times 100, and that will convert it into a decay rate. Let's see how this works. So let's say 1 minus 0.15 is 0.85. 0.85 times 100 is 85%. 1 minus 0.98 is 0.02. 0.02 times 100 is 2%. So this is how we would take a decay factor and turn it into a decay rate. Again, rates are how things are reported almost always. Factors are what you have to plug into your equations when you're trying to figure out exponential growth and exponential decay. Now, we can't talk about exponential relationships without talking about the rules of exponents. So let's take a look at the rules of exponents and some quick little examples of how they work. All right, so the first rule of exponents, and the easiest one to follow, is if you're multiplying two bases together. Oh, I guess we should talk about that too. The number, this number right here, this is called the base. The exponent is obviously called the exponent, right? And so if we have the same base, in this case we have a to the x, and we're multiplying it times a to the y, we are going to keep the base the same. It will remain the same, but we will add the exponents. So a to the x times a to the y is equal to a to the x plus y power. Well, how does that work? Well, if I have r to the third and I'm multiplying it by r to the fifth, notice how the bases are the same, so we're going to add the exponents together. So we still have the base of r, 3 plus 5 is 8. So r to the third times r to the fifth is equal to r to the eighth. The next rule of exponents that we're going to talk about is when you're taking a power to another power. Notice how this looks very different in form. So if we, from the first one, so if you have this exponent right next to a parenthesis, and there always has to be a parenthesis here, you're not going to add them together, you're going to multiply the exponents together. So if I have a to the x to the y power, then we'll have a to the xy power. In practice, if we have t to the fifth, if we take it to the third power, we'll have t to the 15th. Now, what happens if you have an exponent of 0? Well, anything to the 0 power is always 1. So if I have 10 to the 0 power, that will simply equal 1. What happens if you have different bases? So notice how that's different from this first rule up here. We have a base of a, we have a base of b, but the exponents are now the same, x and x. What we can do is we can multiply the two bases together and keep the same exponent. So if we have a to the x times b to the x, that will be equal to a times b to the x power. So if we have 4 to the third times 5 to the third, well, 4 times 5 is 20, and we'll keep the exponent of 3. Well, if we can have exponents of 0, we can probably have exponents that are negative. If we have a negative exponent, it's never proper to give an answer with a negative exponent. It always needs to be converted to a positive exponent, so we need to figure that out. Negative exponents do not produce negative numbers, they'll produce a fraction. So a to the negative x is equal to 1 over a to the positive x. So notice how once we turned it into a fraction, the exponent became positive. For example, if I have g to the negative fourth, that would be equal to 1 over g to the positive fourth. Now, incidentally, this will work in reverse too. If I had a negative exponent in the denominator, that negative exponent would move this base up into the numerator. Finally, what happens if you're dividing bases, the same base with exponents. So a to the x divided by a to the y, well, division is the opposite of multiplication, isn't it? And in multiplication, we added the exponents. What's the opposite of adding? Subtracting. So if I have a to the x and I'm dividing it by a to the y, I will have a to the x minus y power. For example, if I have h to the 7th and I divide it by h to the 4th, that will be equal to h to the 3rd, because 7 minus 4 is 3. So this is a quick, very, very quick overview of the concepts we've learned. Very little practice in here, I understand that. But we are going to have some problems in the review assessment that you can practice these overarching concepts. Before you do that, please, you are expected to take a look at the second video that I've posted that will be talking about exponential relationships and COVID-19. All right. I hope you're able to finish or put all of your notes in your note catcher, and you will be expected to send me a picture of all the notes in your note catcher. Once that's done, go to the next video.